Welcome everybody to my presentation for the CurlUp 2021 meeting, which is going to happen next weekend. And I volunteered to talk a little bit about my experiences in interfacing Rust code from C, which I did in the last weeks while developing modtls. It's an ongoing project, so it's not finished. It's just where we're currently at. This talk is intended for C developers with limited Rust knowledge, like myself. And the project I'm working in, you might have heard of it, is an initiative by the Internet Security Research Group, the parent company of Let's Encrypt. And the goal is to develop a replacement for the TLS SSL implementation in the Apache server that is memory safe using Rust, and especially the Rust TLS named Russell's library. modtls is the module which is developed, and it uses this component to bring a memory safe variant into the server for people who have an emphasis to showcase the technology and to gather experiences. The whole setup, as you can see, is we have Apache, which loads like any other Apache module, modtls, and that incorporates Russell's. It's a C API on top of Russell's, which itself gets Russell's in. So you have like the C world with Apache and the module, and the Rust world then with Russell's and Russell's. And the use of Russell's, from my perspective, is like from C. You call it like any other C library, basically. You have functions, you have header files, you have a library to link against, and you call the functions, get things back, the TLS connection context, you set the ciphers and certificates, and so on and so on. So it's not, from that perspective, not really different than calling another C library. The making of Russell's, the C API, that's where the real work in this project is happening. Russell's is mainly developed by Jacob Hoffman-Andrews. It's one of the key guys from Let's Encrypt, very smart person. And I help him out here and there and make proposals about the API changes and what the application needs, basically. The first thing you're probably interested in, and I didn't want to save it for the last, is like, what have we achieved so far? Cup of coffee. This is a measurement I did on my machine, my development machine on the Mac OS. And what I did here is I pulled 1 million requests over connections of files, which is like the least performance for the server to serve a static file, so we can measure what the TLS stack itself really is up to. Dragging 1 million requests from my created 1,000 files of different sizes, from I think 10K to 10 megabytes, so to have some variation in there. And I measured how many requests per second we get through. The first is that uses only a single connection. And then we have 4 parallel connections and 16 parallel connections to see how this all scales up. On the one connection case, you see that modSSL is faster than the modtls implementation, but if you use parallel connection, you see that we have a slight advantage on using modtls. So in summary, I would say we can achieve comparable performance. The real performance is of course a matter of your installation, of your hardware, of many, many things. And these numbers, like all benchmark numbers, are to be taken with a heavy grain of salt, because what is not visible here is like the memory usage of both modules is different. I think, if I remember correctly, modSSL, when we pull these is at around, on my machine, on around 50 megabytes of RAM, which it uses for a process, and the modtls is about half of that. Which means several things will or might fit much better into the CPU caches, and that will affect performance, especially when you have parallel processing. So it's hard to say what it will exactly do on your machine, on your setup, and don't hold me to it. But I can say, I think with confidence, that we have comparable performance, as I said. So why do we have this C Russells, this Crussels thing, and why do we need that? And what does it exactly do? And what is easy or more hard about it? You have to imagine that C and Rust are really two worlds which have certain things in common, but also major differences. Which is no surprise, because Rust makes memory safe assumptions as its core mission, and C is not exactly focused on that. A lot of history you might have read about several things, and what advantages, disadvantages, and so on and so on. In general, you can say like C is like if you say so to the programmer. In C, I can cast anything to anything, and if I tell the C program, treat this pointer as a character pointer or as a pointer to a structure or whatever, the C compiler will oblige. In Rust, this is not possible per se. Rust says, wait a minute, this can't be right, I won't accept this, you have to specify more clearly what you want to do here. So in Rust, you have to think more in advance about your memory issues, about your handling, especially about mutability of things, like in C you would say constness of things. In your design, you have to care much about it, because the Rust compiler won't let you change your mind afterwards. In C, you have sometimes the talk has been of const cancer. If you have a C project and you introduce constness as a later thing, for example, you end up with having to call other functions or libraries which do not declare parameters as const, and so you have to cast a const thing to something which is not const, and so on, and you have to break even those assurances, and that's sometimes dangerous. But in Rust you have no choice, you have to think about it from advance, which saves you the debugging afterwards, of course. So it's from my perspective a worthwhile investment. Complexities generally of a multi-threaded application of course remains, but when you think in advance of it, and the compiler like Rust compiler helps you with proving your assertions, it hurts much less as when you have obscure memory bugs afterwards when you have made a release. Constness, like in C, is limited. You can have a struct with a mutable member, like here, name, and you can pass a const pointer. But that doesn't mean that the member is constant. You can still modify the member which is not declared const. In Rust, this is not the case. In Rust, in general, it has a basic core assumption. One thing can only at the same time be true. Either you have one or more references to something, like a resource, like a struct or so, and these references are immutable, or you have exactly one mutable reference, and no one else has a reference to it. And that makes access to memory safe from the beginning, but you have to think more about, like, when is my structure really changeable, and when you hand it out to other parts of your application to use it, it is by default, if you don't do anything special, it's constant and no one can modify it, which makes it safe to use, of course. Just example here, if you make a similar structure in Rust with a member, the constness or mutability handles the whole struct and its members. So when you pass a const simple, the name is also not mutable. There are exceptions in Rust to this and how you can get around it and so on, and special things which I will not go into in this talk. But in general, if you don't do anything special, this is the case. There are also in Rust markers only on a type which assure that instances of this type are safe for multi-threaded use. They're send and sync. And sync means it's really thread safe, to give a short explanation. And send means you can transfer an instance to another thread, so it's not bound to the local thread. There are no real analogies in the C language for this, as far as I can tell, at least not plain C. So if you bring these two worlds together, so you want to use Rust code from C, you have something which builds a bridge between these two worlds. Because when you pass C data in, the C data does not obey Rust rules, so Rust cannot make assertions, and the Rust compiler cannot really guarantee the memory safety. So it will be unhappy about this. So you need something which sits in between and brings C data into the Rust code where under the condition that Rust can make its analysis of the code and assure the safety. And since C has no knowledge of Rust, but Rust has knowledge of other foreign languages, and they have a mechanism which you might have heard also, which is the unsafe feature in Rust. And unsafe gives a coder which writes Rust code some superpowers. In unsafe Rust code, you can dereference a raw pointer. You can call other unsafe functions or methods. You can access or modify a mutable static variable, as I said, like that would mean, which is normally forbidden, that you have multiple globally visible mutable variables. You can implement an unsafe trait. Trait is something in Rust like, you can think of it as an interface abstract base class, except it isn't really, but something similar. Access field of union. So you mark code in Rust as unsafe, which like the unsafe keyword, and you make curly braces for a block, and this block is then unsafe. In this example, you have declared a Rust function with C-compatible interface to the outside, U16 min, which U16 is the simple type in Rust of an unsigned 16-bit integer, and you bring in from outside a pointer to an array of these U16s and a lang indicator and get something back, assuming the minimum value of this. To take this nums pointer here into Rust, you have to have an unsafe block, and in this unsafe block you see here slice from raw parts, and that's a Rust construct which lets you take a pointer and a length indicator and constructs a Rust array, so to say, of fixed length. And that then you can use in Rust like any other Rust array, for example, to iterate over it. So this is the basic feature that Crustles has to do. It has to provide functions which C can populate with parameters, and it has to take the functions in a safe way to make them Rust types. So Rust knows what the mutability, the constness, and everything else about these types in order to handle them then in safe parts of Rust. You can also pass, of course, Rust data out. Here's a static immutable variable. This is a string of U16, so it's 8-bit unsigned character, basically, we would say unsigned char. And you can declare a function getMessage, which returns the message array as pointer. It's also a construct in Rust. You can take basically the address of a thing with the S pointer. Here you don't need anything unsafe, because S pointer is always possible. So you can make something, Rust thing, to a pointer. The other way around is unsafe, to take a pointer and convert it to something in Rust. The current state of things in this is that you have to be a little bit careful. You can make mistakes like this one, which is not using a static anymore, but using a variable message string from hello, and you return message as a pointer. And like everyone who writes C for some time has probably at least once done this mistake. This code will return a pointer on the stack. Message is a variable that gets deallocated when the function returns. In Rust, most allocations, when possible, happen on the stack anyway, so this will be a variable on the stack, most likely. And you take the address, which is fine with Rust, and return this address, which is also fine with Rust, but the address no longer points to something valid. One would wish in Rust to have a little bit more support in this area, so that you can handle pointer or make assumptions about pointers, and you get a warning one would wish for in Rust when you do things like this. And there's certainly things which can be improved in this bridge code to have more support, and it's worth looking into. The good thing about this bridge code is, like most memory layouts between C and Rust are one-to-one. For example, if you have arrays of simple types, arrays of integers, arrays of pointers to other things, and so on, these are, from a memory layout point of view, the same between C and Rust, and that makes exchange of data of certain types very easy. So you don't have to copy everything. You can pass the address of Rust arrays, for example, outside, and have it easily accessible from C. The thing which this conversion, of course, does not solve is the problems of memory lifetimes, initialization, thread safety, where when you pass a Rust pointer out to C for a handle, for example, in the modtls library, you create a server session when you have a connection, a server session of the Russell's code, like a TLS session, and this you handle as a pointer in the C, and you have to, in the end, when you no longer need it, you have to call a free function, like with other libraries as well, and this object you should only access from one thread at a time, for example. These things, these assumptions which the C code has to obey, these are only documentable with a function. You only can write in the comments, like this we give you back as a lifetime of so-and-so, and you have to call free in the end. There's no automatic support there for some things which you wouldn't expect, but there's also no standardized way of making attributes to such a pointer. That would be sometimes nice. A pointer in Rust, the documentation says the precise rules for validity are not determined yet. And that's something in Rust. In general, it's an ongoing thing. It's a living language. It's developing. Features are in there with like a nightly tag, like as an experimental feature, and some things are discussed how to handle, and I come back to more of that later. So for pointers, Rust pointers are never null. They must point inside an allocated object. Access is not atomic, and casting is valid as long as the object is alive. And that's the example from the previous example. We had taken a pointer of an object, which then went out of scope, and we still had the pointer value. And casting it back to something is, of course, would have not been allowed, so to say. So this I talked about, the pointers, the handling, the documentation. There's another thing which has gotten attention recently, a thing in Rust, and that is called panic. Panic mode. Panic. Rust can make, the compiler tries to make a very good analysis of your code, like is it all the lifetimes, are they okay, does it fit, the mutability, blah, blah. But one thing, there are several things where Rust code cannot make assertions at compile time. And a famous example of that is, for example, memory allocations. So if your process runs out of memory and Rust is unable to get the memory it needs, it panics. That's Rust's defined way out. It meets a condition, it runs into a condition which it can no longer proceed, and there's a panic. There are other places where panics can happen, not only out of memory. And the standard behavior in panic is to unwind the Rust code, the call stack which you are in. And if no one does anything, it terminates the thread. And if the thread is the main thread of your program, the whole program will terminate. And this is currently having very much focus because there are proposals to bring Rust into the Linux kernel. And Linus Torvalds said, it's all very interesting to him and he's not opposed to something like that, but bringing in code into the kernel that can panic is simply a no-go. And you can imagine that it would not be nice if your operating system just crashes your computer completely because some assumption has been wrong. So what does it mean for bridge code? There is a way to catch these panics. It's called a panic boundary, so to say. And so the call stack which caused the panic is unwound, which means all allocated resources are freed. And you have this, like in other languages, an exception catch phrase, where you can, stop the panic from going further up the stack, and which means the bridge code in this case has to catch it and return an error code. So the application can know that this call did not succeed and maybe get a code which tries to give some hint about what the root cause is, like out of memory or something else. Which means Rust internal APIs or between Rust components, they don't do this. So they have a lot of functions which do not have an error code because they have only valid return values all the time, and panics will just pass out. No one is handling those because they're, I don't know, not supposed to happen. I'm not sure. The thing is, in the bridge code, you need to do that. You cannot say the application, oops, we ran out of memory, or we encountered some weird things and the whole process crashes. That's not really acceptable. And how common are these panic situations? Well, the fuzzing community started to writing Rust fuzzers. Initially, you would say, like, what, fuzzers for Rust? Rust is memory safe. And that is still true, but it's not panic safe, so to say. So people are fuzzing Rust components and trying to make them crash, just like C programs. They feed Rust some garbage input, and if the Rust component makes some invalid assumptions internally and panics, they catch that and say that the Rust program has crashed. I link a video here from a talk, a presentation about Russell's fuzzing. I put the links under the description of the video, I guess. So panics are, from our C programmer's point of view, a little bit like null pointer dereferences, segmentation faults, which we have in C program. When you have a null pointer and try to use it without checking, and you get a bus error, segmentation fault, and your program crashes. And why do we have that in Rust as well? In Rust as well? possibly, is like you have a common problem in programming that you have to initialize certain things in steps. So you have, for example, a structure with two members, and you cannot initialize them both at once. So the possibility is that one of them is missing, or both are missing when you do it. And in C, you would, for example, have pointer members, which are initially null, and later you assign them values, and then everyone uses these values, A and B, these members of the structure. And in Russell's, the equivalent is, because you remember Russell pointers are never null, Russell's has something that is called an option, and that can have a value or it can be none, as Russell calls it. So you can declare this. This structure has members that are options, so they can have a value or not. And in Rust, you use them like this on the left side. You say, when you try to access the member A of X, match XA. If it is something, some value, then do something with the value. If it is none, then handle the case that it's missing. And if you have a lot of options, that can become, of course, a little bit tedious to always do this match. So when you are certain in Rust that the value is there, you can just call unwrap. And of course, you can imagine that if your assumption, the programmer's assumption, that there is indeed a member A with a value is wrong, this unwrap panics. So this is like, I would say, like a null pointer dereference. The difference is, once this happens, the panic damage can be limited. The panic, as I said, unwinds the code stack. The bridge code can catch it. So as a result, in the modtls case, you lose, when such a panic happens, you lose one connection, which is then aborted, instead of losing a whole child process in the server. And that's a huge difference when it comes to crashing your server by sending it garbage from the outside. So it's a good thing. More to the basics is when you write this bridge code in like in Crussels, there are tools available that generate a header file, which you can use from your C application. The tool Cargo, for Rust that builds everything, can also build a library which you can link. And there are some things which the Crussel project found out. For example, we have now in curl, in the current curl, you can bring in two Rust components, the Russell's SSL stack and the Hyper HTTP implementation. And when you have that, you have to take care that you do not have duplicate symbols, because when you link such Rust bridge code and its component into a library, it pulls in all the Rust component it needs. So if you build two libraries, you have most likely duplicate Rust components. So there needs to be some care about visibility of things. So what to make of it all? My impression, and that's really my personal impression of things, is Rust brings new important expressiveness, which means as a programmer you can specify much more what you expect your structures, your code, how it is to be used, how you intend it to be used, so that the compiler can analyze your assumptions and point you to places where your code violates them. In C, you find out these violations most of the time, or often, when you get a bug report on a release thing, and then you have the burden of analyzing this, reproducing this, and so on and so on, which is very tedious, and that's experience from maintaining C code like everyone has. That's an unpleasant experience which we would like all to avoid. So the expressiveness in this regard that Rust brings is very, very, I think, needed and necessary, especially when you have an application that is multi-threaded and a little bit performance sensitive. Rust itself, I found, is not the easiest to learn. The basic language features is readable, but there are very many subtle features when you go above the usual mutability Constness things that are in the language, and there's a huge area of things to understand. It's not, of course, this is true for every new language you will learn, but I think if you want to really understand Rust code and write Rust code, you need to bring a model of how memory and machine operates. It's advertised as a system programming language, and that's true. It will never be an application language in that sense that Python is, for example. The unstableness of Rust as a language is good and bad. The bad thing is, of course, you can expect maybe that in a couple of weeks or months' time, they will make a major change, and you have to recompile everything again, hopefully without having to change yourself something in your code, what might happen. So it's a moving target, and the good thing is, of course, that it's an opportunity to bring in requirements, like, for example, when you integrate it into a C application and have special needs or identify needs for that. For example, there's support for what to do with the pointer value, what are you allowed to do with it. Memory safety is definitely necessary. I mean, everyone who maintains a C or any project knows that these things are nasty, and not just from the damage they do, but nasty for us programmers to analyze and find the real cause. Yeah, concluding thoughts. The work is very nice and very fun. The people are very supportive. Not only Jacob, who's writing Russell's, although the Russell guys are always there when you have questions. And I hear the same from Daniel when he talks about the hyper work he does. So don't let these culture wars, which are sometimes seen on the web between a C camp and the Rust camp, don't let that hold you back. The persons are all approachable and nice, and these culture wars are, in my opinion, simply silly. I think the way forward for developing components for the internet is the language needs to evolve in a way that these management of memory becomes more easier, in a way that allows you at the same time to write code that is very close to the system and very performance sensitive. So in that way, the scope of Rust is, I think, very, very good. If Rust, what exactly all needs to change and how it will develop to incorporate all this, I cannot say. There are many people way smarter than me in this field, and but I think the direction is definitely needed. And if Rust is not the thing, I think these features will definitely make it into the mainstream in some other way. It's definitely necessary. And that's it from me for today. I hope you found some interesting things in this. I will be on the Curl-Up meeting next, I think Sunday it is, and looking forward to any questions I might answer to you. Thanks a lot. Bye-bye.